All right, so today we're going to deep dive into this research paper making waves in the AI world. It really tackles a question that's been bugging researchers. How do we get large language models, those impressive AI things, to catch their own mistakes?
It's kind of like if you had a star student, one who breezes through complex equations, but sometimes they, miss a simple arithmetic error. They've got the
Yeah.
knowledge, but using it constantly for self-correction, well, that's a whole other beast.
Yeah, that's a great way to put it. And this paper brings us a new method. They call it SCORE, which stands for self-correction via reinforcement learning. The exciting part, we don't got to spoon-feed the model the corrections. It learns to be its own critic.
What really grabs you is the idea of intrinsic self-correction they highlight in this paper. It goes beyond just giving the model a set of rules. It's all
Really?
about helping it grow its ability to spot and fix errors on its own based on what it understands about the problem.
So it's like we're not just teaching a student to just solve the math problem, right? We're teaching them to double check their work, to think through any inconsistencies they find on their own.
Exactly. And the paper lays out why that's such a tricky thing to do. Traditional methods, like just asking the LLM to self-correct, well, they haven't really worked out that well. Turns out these LLMs need a more structured approach to grasp the whole self-correction thing.
It's kind of like asking someone to proofread, but without any guidelines or strategies. Sure, they might catch the glaring errors, but anything subtle, poof, gone.
Right. And they dig into the weaknesses of another common method, supervised fine-tuning. This is where you train the LLM on examples of, corrected responses, but often it leads to what they call distribution mismatch.
Distribution mismatch. Gotta admit, that sounds a little intimidating. Can you break it down for us?
Okay, picture this. You're training a student using only old exam papers. They might ace spotting errors specific to those exams, but then you hit them with new problems, stuff they haven't seen, or their own unique mistakes. They struggle. That's distribution mismatch in a nutshell. The model gets too hooked on those specific examples, and then can't generalize its self-correction skills to fresh situations.
So they're not really learning to self-correct. They're just mimicking the corrections they saw in training.
Exactly. And there's this other pitfall with supervised fine-tuning. They call it behavior collapse. It's like that student who, instead of, really understanding and correcting thoughtfully, they just reword stuff superficially to match the answer cue, dodging the hard work of real self-reflection and improvement.
Okay, so we've seen that simply telling LLMs to self-correct or showing them examples doesn't cut it. They need a more, I guess you'd say, sophisticated approach to really develop this skill, right? Enter SCORE. Can you tell us more about how this method tackles these issues?
So SCORE uses this two-stage training process. It's pretty clever. In the first stage, the focus is on something they call decoupling attempts. Basically, they train the LLM to give a good second attempt at the problem. But, and here's the twist, they intentionally keep that first attempt pretty close to the original, the uncorrected one.
Huh. That sounds kind of counterintuitive. Why not shoot for improvement right from the first try?
Well, remember that behavior collapse we were talking about. If you push for both attempts to be perfect off the bat, the model might get stuck on making that first attempt flawless, and then, barely change anything in the second. This decoupling, it forces the model to really wrestle with revising and refining its first response. That's what leads to more substantial and, I guess, meaningful self-correction.
So it's kind of like saying, hey, your first draft, it's going to have some mistakes, and that's all right. But really look at it, analyze it, and come back with a second draft that's significantly better. You're encouraging that crucial revision process.
Exactly. And they do this decoupling using a particular kind of reinforcement learning that has this neat constraint built in. This constraint makes sure the first attempt doesn't stray too far from what the base model would normally do.
Oh, I see. So it's like giving the student a safety net, but still encouraging them to try out different ways to self-correct.
Yeah, it's all about balance. Pushing exploration, but keeping that foundational knowledge in sight. But where school truly shines is in the second stage. That's where they bring in something called reward shaping.
Okay, tell me more about this reward shaping and why it's so important in this stage.
So in this second stage, now the challenge for the LLM is to make both its first and second attempts the best they can be. But the cool part is how the model gets rewarded. It doesn't just get a gold star for a correct final answer. It actually gets bonus points for every time it goes from a wrong answer to a right one.
So it's like you're saying, hey, We see you're learning from your mistakes, and we're going to reward you for that effort, even if the first answer wasn't spot on.
Exactly. It's like encouraging a student to show their work, right? To show that they understand the process, even if they tripped up on the solution initially. This approach encourages the model to not just focus on the end result, but on that journey of improvement.
It sounds like this reward shaping is key to helping the LLM build a real self-correction strategy. It's not just aiming for a good first answer anymore. It's learning to critically assess and refine its thinking to get those more accurate results consistently.
Precisely. And the results speak for themselves. Remember those gains on the MATH and HumanEval datasets we mentioned? A big chunk of that success is thanks to this innovative reward shaping. It pushed the model past just copying patterns in the data towards really understanding how to find and fix its errors.
It's amazing how they managed to instill this intellectual honesty in the model, encouraging it to not just want the right answer, but to actively engage in that self-correction process.
Yeah. It's a huge step forward in AI development. And what's even more exciting is that this ability for self-reflection becomes even more crucial as AI systems get more complex and powerful. It's about AI becoming not just smarter, but more reliable, trustworthy, and, beneficial for everyone.
Absolutely. It feels like this research is opening up a whole new frontier in AI, with applications way beyond just LLMs. Before we jump into those broader implications, I'd love to dig deeper into those challenges they faced developing this method and why those traditional approaches just didn't work. Seems like they really pushed the envelope here.
Oh, you're absolutely right. This research goes deep into some really complex stuff, and understanding those hurdles is key to appreciating what they found. Let's take a closer look at some of those challenges in the next part of our deep dive.
So we were just talking about how those traditional methods haven't really cracked the code of teaching LLMs to self-correct. Before we get into score success, those hurdles the researchers had to jump over, those really intrigue me.
Yeah, one of the big ones was finding that balance, encouraging the LLM to try different things, but also making sure it doesn't wander off too far from, its core knowledge. Remember that decoupling stage where the first attempts kept close to the base model's initial response? Well, getting that right, that was no walk in the park.
I can imagine trying to walk a tightrope between, sparking creativity, but keeping that solid foundation. How did they find that sweet spot?
They used this clever mix of reinforcement learning and something called Xiaol divergence regularization.
Xiaol divergence. Sounds pretty technical. Any chance you could give us a simple analogy to help us grasp it?
Think of it like training wheels on a bike, Xiaol divergence, it acts as a constraint. It stops the model's first attempt from going completely haywire, too far from its initial understanding. It's like a safety net. Lets the model experiment with different self-correction approaches, but keeps it grounded.
Okay, I think I'm getting it. So it's like the LLM's got the freedom to explore, try new things, but without totally wiping out. But how did they actually use reinforcement learning to, guide the model's learning here?
It all comes down to rewards, right? In this case, the model gets rewarded for coming up with a good second attempt. Through trial and error, it figures out which changes lead to better results. Essentially, it learns how to self-correct better to rack up those rewards.
It's almost like the LLM is playing a game, trying to score points by making the best corrections.
Exactly. And the researchers, they found that this decoupling stage, with its careful balance of exploration and, constraint, it was absolutely essential for score to work. If they skipped it and went straight to optimizing both attempts at the same time, well, the model often fell into that behavior collapse trap we talked about, just superficial tweaks, no real understanding.
So by first training the LLM to make substantial changes in that second attempt, they essentially laid the foundation for, more meaningful self-correction later on. It's fascinating. They had to, in a way, trick the model into learning this valuable skill.
Yeah, building that foundation of self-reflection and analysis, that was key. Once the model had mastered this decoupling, it was ready for the second stage. That's where the real score magic happens, the reward shaping.
Now, remind me, how does that reward shaping work again? And why is it so crucial in this stage?
Okay, so in the second stage, the focus shifts to making both the initial and the revised attempts the best they can be. But the real brilliance is in how they reward the model. It's not just about getting a good job for a correct final answer. The model gets bonus points every single time it goes from a wrong response to a right one.
Oh, so it's like saying, hey, good on you for learning from your mistakes. We're giving you extra credit for the effort, even if the first answer wasn't perfect.
Precisely. It's like encouraging a student to show their work, to demonstrate that they understand the process, even if they stumbled a bit on the way to the solution. This approach, it really pushes the model to focus on that journey of improvement, not just on getting the final answer right.
It sounds like this reward shaping really helps the LLM build that true self-correction strategy we were talking about. It's not about just shooting for a good initial answer anymore. It's about learning to really look at its own thinking, refine it, to consistently hit those accurate results.
Exactly. And the results they got, they show just how powerful this approach is. Remember those big improvements on the MATH and HumanEval data sets? A huge part of that is because of this reward shaping. It's innovative. It pushed the model past just copying patterns. It helped it actually understand how to spot and fix its own mistakes.
It's like they instilled this intellectual honesty in the model, encouraging it to not just want the right answers, but to actually dive into that self-correction process.
Yeah, it's a major leap forward in AI development. And what gets me excited is that this whole self-reflection thing, it becomes even more vital as these AI systems get more complex and powerful. We're not just talking smarter AI, but more reliable, more trustworthy, really beneficial for everyone.
Absolutely. It feels like this research is opening up a whole new world in AI, applications way beyond just these LLMs. Before we get into those bigger picture implications, I'm curious about the actual results, the nitty-gritty. Can you tell us more about the problems they tested score on and how much improvement they saw?
Of course, let's dive into those exciting results and see how well this new method actually performed. So the results, pretty impressive. They put score to the test on a bunch of benchmark data sets. You've got the math data set, that's for solving math problems, then the MBPP and HumanEval data sets for code generation, and across the board, score consistently outperformed other state-of-the-art methods for LLM self-correction.
That's a pretty bold claim. Any specific examples of the kind of improvements they saw?
Yeah, on the math dataset, score bumped up that self-correction rate by a whopping 15.6% compared to the base model. That's a big jump, in terms of the model actually finding and fixing its own math errors.
So we're not talking about some tiny tweak here. This suggests these models could become way more reliable, more accurate at tackling those tough problems.
Exactly. And get this, score also pulled off a 9.1% gain on the HumanEval coding benchmark. That one's designed to test if the model can create working code based on natural language descriptions and those improvements. They really hint that score isn't just a one-trick pony with math. It's got broad applications. It can handle different domains.
That's really exciting. Sounds like they've really pushed the limits of what's possible with this LLM self-correction thing. But I imagine you guys don't stop at just impressive numbers. What are the bigger implications here? How could this tech reshape industries, the way we interact with AI, all that?
Oh yeah, the applications. They're vast, really exciting. Just imagine self-correcting LLMs in healthcare systems, helping doctors with diagnoses, treatment plans, constantly learning and refining their understanding of all that complex medical data.
It's kind of mind-blowing to think how this could change fields like medicine, where even small mistakes have huge consequences, and the potential benefits. They got to go way beyond just healthcare, right? What other areas could be impacted?
Finance, think about that. Self-correcting LLMs, analyzing market trends, managing investments, assessing risks, you name it. Helping folks make smarter financial decisions. They could even help spot fraudulent activity super accurately. And in education, think personalized learning, tailored to each student's needs, with LLMs giving real-time feedback, adapting their teaching based on how the student's doing, their understanding.
It's incredible the way we learn, work, interact with the world, all transformed by these advancements. But we got to address the elephant in the room, the potential risks. As we bring these super sophisticated AI systems into our lives, what worries should we keep in mind?
Well, with any powerful tech, the biggest challenge is making sure it's used responsibly, ethically. As LLMs get more involved in those critical decisions, we got to tackle those issues of bias and fairness head on. It's crucial that these systems are trained on data that's diverse, representative. We don't want to perpetuate or amplify existing societal biases.
That's a great point. It's not just about making AI smarter. It's about making it fair, equitable, making sure it lines up with human values.
Absolutely. And as these AI systems get even more capable, transparency and accountability become super important. We need to know how they reach their decisions, right? And make sure there are ways to hold them accountable for what they do.
Just like any tool we create, it comes down to using it wisely, thinking about the potential impact.
Exactly. The future of AI, it's a reflection of the choices we're making right now. It's our responsibility to guide its development, to make sure it benefits all of humanity.
That's a powerful thought. This pursuit of artificial intelligence, it's not just about pushing the tech forward. It's about shaping the kind of future we want to live in.
Well said. And this research on self-correcting LLMs, it's a step in the right direction. It's about developing AI that's not just smart, but reliable, accountable, truly a force for good.
Well, on that note, we've reached the end of our deep dive into the world of self-correcting LLMs. We've unpacked the SCORE method, seen those remarkable results, talked about the amazing applications, and the ethical stuff we can't ignore. Hopefully this deep dive has given you some insights, sparked some curiosity about where AI is headed. Remember, the conversation doesn't stop here. Keep exploring, keep asking questions, and let's keep talking about how we shape the future of this game-changing technology. Until next time.